Welcome back. We're in section 7, next to the last section in chapter 11 on probability. Remember the last time we talked about events involving or? Well, this time we're going to be talking about events talking about and instead of or. Remember, or represents union for set notation and represents intersection. That should give you a little bit of an idea of what's going on. And we'll talk a little bit about conditional probability. If it sounds complicated, it really isn't, especially when you're working with tables. Excuse me. So find the probability of one event and the second event occurring. Notice the word and. Compute conditional probabilities, that's second objective, and here we go. So first of all, what are independent events? They're ones where neither of them affects the probability of the other. If they're independent, then all you need to do is multiply the two individual probabilities. Done. So what about independent events? Well, let's look at a US roulette wheel. 38 numbered slots, 1 through 36, 0 through 0, 0 and 0, 0. 18 are black, 18 are red, those are the 36, and the two unusual ones are green. The ball can land on any slot with equal probability. What's the probability of a red on two consecutive plays? So one of the important things is they're independent events. Regardless of what happens on the first roll of the roulette wheel, doesn't affect the second one. The second one occurs as if the first one never occurred at all. So they're independent events. A red on a play, there are 18 red slots. 18 are red. 38 all together up here. And so we reduce that to 9 over 19. And the probability of red occurring on both, since they're independent events, just multiply the two probabilities. In this case, they're exactly the same. And you get about 81 over 361, or around 0.224, or if you like, 22.4%. In a family, what are we talking about here? We're talking about babies being born, and the probability of a baby girl is about 1/2. Actually, it's a tiny bit under 1/2, but as far as we're concerned, to make things simple, we're going to say it's exactly 1/2. So the probability of 9 girls in a row is used as a factor 9 times. Why? They're independent events. Regardless of what the first 3 babies are, the next one is either a boy or a girl with 1/2 probability. So multiply all those 1/2s together 9 times, because we're talking about 9 girls in a row. So there's your multiplication. Of course, it'd be a little bit easier if you took 1/2 to the 9th power. And it's 1 over 512. Of course, you don't see that too often. Number one, you probably don't see too many families with 9 children. And number two, all 9 of them girls is, as you can see, not something you'll see too often. How about hurricanes? Let's take a look. Let's suppose the probability that South Florida will be hit by a hurricane in any year is 5 over 19. Just a little bit over 1/4. In other words, about 1 every 4 years, roughly speaking. Or about 5 every 3 years. Anyway, that's your probability. What's the probability you'll be hit by a hurricane in 3 consecutive years? How do we solve that? Well, we have the same thing happening 3 consecutive years. The probability for each one of these is 5 over 19. They're independent events. As far as we know, a hurricane hitting this year won't affect whether a hurricane hits next year or not. So just multiply those 3 probabilities together since they're independent, and you've got your answer, about 1.8%. Well, if you're in South Florida, it's a little consolation, but 3 consecutive years, that's really scary. There still is almost a 2% chance of that happening now. How about the probability you'll be hit by a hurricane in any single year? Is 5 over 19. What do we want to know? What's the probability will not be hit by a hurricane in the next 10 years? This sounds a little bit tricky, right? How do we solve it? Well, will not be, remember, either it is or it isn't. Those are opposites or complements of each other. So the probability of no hurricane is 1 minus the probability of a hurricane. Decimal if you like. So the probability of not being hit by a hurricane is 14 over 19. 10 years in a row. In other words, you've got 10 years without hurricanes. What's the chance of that? Well, we'll use this 10 times. Only about 5% chance of going 10 years straight with no hurricane. How about dependent events? We've been talking about independent events. How about dependent events? This is where when one happens, it changes the probability of the other one. We're talking about A and B, and they're dependent events. Then you multiply the probabilities if this is the thing that changes it. A has already occurred. So take the probability that A happened, multiply it times the probability of B happening, and you can get it. So let's take a look at an example then. Free trip to Madrid, and you can take 2 people with you. However, 10 of your cousins appeared out of nowhere, and they really want to go. How do you do that? Well, you could play favorites, but let's not do that. Let's put each name on a card, throw the cards in a hat, pick one name. Then you pick a second name without replacing the first card. Very important. Second name without replacing the first card. If you replace the first card, these card selections would be independent, but you're not replacing it, so the probability changes on the second one. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. So how do we do that? We want probability to speak Spanish times the probability of the Spanish cousin was selected first. Here's the probability that on the first card This is card number 1. You pick the Spanish-speaking cousin. Now that changes things because then you've already selected one. You've taken that card out, so there are 2 Spanish-speaking cousins left and 9 cousins total. Multiply those 2 probabilities and you end up with about 1/15 or 0.067 or almost 7% chance of choosing 2 Spanish-speaking cousins to go on the trip with you to Madrid. On to another example. We're picking 3 people at random, 1 person at a time, and you've got 5 freshmen, 2 sophomores, 4 juniors. We want the probability that the first 2 people selected are freshmen and the third is a junior. First of all, figure out this one. First 2 are freshmen. Well, here's the probability of picking a freshman first. Remember that one of those freshmen is gone, so you only have 4 left, 10 total left. So here's your probability for getting the 2 freshmen. They're dependent. You're going to multiply those 2 together. What is the chance of the third one being a junior? Well, there's only 4 juniors and you have 9 students left because you've already picked 2 out of the 11. Multiply those 3 together and there's your probability. The first 2 were freshmen and the third is a junior. So now this is a little bit different from what I'm accustomed to. Typically, if you want the probability of an event B, assuming an A has already occurred, all the other books I've ever seen has it written like this instead. The probability of B, given that A already happened. So you can use either notation you like, whichever helps. This is the probability of B if A has already occurred. So maybe an example here. You're selecting a letter from the letters of the English alphabet, 26 letters of course. What's the probability of selecting a vowel given that the outcome is a letter that precedes H? So this is how it looks. And this one turned out right. Okay. So I guess that might have been a typo in the last one. We're looking for the probability of a vowel if the letter precedes an H. In other words, a vowel if you've got an H right after it. Well, the sample space is restricted to the set of letters that precede H. So it's A through G. If it precedes H in the alphabet, there's 7 possible outcomes. And these are the 2 possible vowels. You had 7 possible outcomes, so there's your conditional probability. Now, using a table, little bit easier actually. Mammography screening on 100,000 U.S. women aged 40 to 50. So here's the table, and what you want is, assuming these numbers are representative of all U.S. women, find the probability of the woman in this age range, and that's all we've got here, 40 to 50, has a positive mammogram if she does not have breast cancer. Now this is the given. What's the probability for these? In other words, this is what we're looking for. What's the chance of getting a positive mammogram even if she does not have cancer? So, positive mammogram if she has no cancer. So we already know she doesn't have breast cancer, and those are 6,944. $99,200 that don't have breast cancer. And so the chance of having a positive mammogram with no breast cancer, here's all the non-breast cancer people, and here are the ones that got the positive mammograms. And there's the chance. Make sure once you get in that age, you do get tested. But know that there are such things as positives. They call these false positives. So even if you get a positive mammogram, get a second opinion, because it could be a positive. It's false. Okay, well that's it for number 7. We've got one more left. We'll be talking about expected value in the next section. So tune in and we'll see you soon.